So, how do you get a rock to think? I'm serious. A modern processor is, at its heart, just silicon. Basically, a rock that we've tricked into doing math. And the secret isn't magic, it's all about controlling electricity. To build a computer's brain, you first have to teach electricity a really simple language. Just two words, stop and go. All right, let's get into it. So that's what this explainer is all about. We're going to uncover that exact story. It's the tale of the transistor and how its simple, incredible ability to switch on and off became the foundation for, well, everything digital. This is the on-off story. Before we dive into the nitty-gritty, just wrap your head around this for a second. Everything your phone or your computer does, from streaming a movie to running a complex program, boils down to billions, and I mean billions, of microscopic little components making one super simple decision over and over again, on or off. It all starts with these tiny gates. Now, if you want to build a gate that you can open and close, you first have to figure out how to build a one-way street, right? You've got to be able to tell electricity which way it's allowed to go. And that's where our story really begins. Not with the transistor, but with its simpler ancestor, the diode. So what is a PN junction diode? Well, think of it as the electronic version of a one-way turnstile at a subway station. It's made by sticking two different types of semiconductor material together, a P-type and an N-type. And the real magic happens right at that junction, which creates a barrier that only lets current flow in one direction. It's pretty much the most basic form of electrical control you can have. So how do you actually use this one-way street? It's all about which direction you apply the voltage. As you can see in these diagrams, if you apply it one way, we call that forward bias. Boom, the gate opens and current flows right through. But if you apply it the other way, that's reverse bias, the gate slams shut and it blocks the flow completely. And what these graphs show, even though they look a little technical, is a really simple idea. In that forward direction, you give it just a little bit of voltage and the current just shoots up. The gate is wide open. But in the reverse direction, the current stays at pretty much zero. The gate is locked tight. And there you have it, our perfect one-way street. Okay, so a one-way street is great, but it's not a switch. The real breakthrough, the game changer, comes when we take this idea and build a better gate, one that we can actively open and close using a separate tiny little signal. We needed to go from just directing current to actually controlling it. And here it is, the bipolar junction transistor, or BJT for short. William Shockley cooked this up back in 1951, and it's basically a semiconductor sandwich. You can see here in this NPN structure, it's a P-type layer that's been squeezed between two N-type layers. This setup gives us not one, but two of those junctions and three terminals to play with: the emitter, the collector, and the all-important base right there in the middle. You know, the name itself is actually a huge giveaway for how it works. A signal is passed from a region of low resistance to a region of high resistance. So the device is effectively transferring a signal across a resistor. You combine transfer and resistor, and you get transistor. It's such a simple, elegant name for a device that literally changed the world. So here's the absolute key. That base terminal, that's our control knob. Think of it like the handle on a water faucet. A tiny little turn of the wrist. A small current applied to the base can control a much bigger flow of water, or in our case, current, gushing from the collector to the emitter. This is the whole principle of amplification, but it's also the secret to how it works as a switch. And that brings us right to the heart of our story, because while transistors are incredible amplifiers, their most profound impact on our world comes from using them to make just two simple decisions: to be completely on or to be completely off. Let's start with the off state. In the world of electronics, we call this the cutoff region. This is the state where we want the transistor to act like a solid wall, just completely blocking the flow of any current. And the main idea here is super simple. In this cutoff region, the transistor is behaving exactly like an open switch. The circuit is broken. The connection between the collector and the emitter is gone, and the main path for the current is totally blocked. So how do we get it into this state? It's easy. We just apply zero or a negative voltage to the base. Doing that reverse biases both of those internal junctions, the emitter base and the collector base, which basically turns them both into closed gates. And with both of those internal gates shut, nothing's getting through. The transistor is off. All right, now for the other side of the coin, the on state. We call this the saturation region. This is where we want the transistor to just get out of the way and conduct as much current as possible, acting like a perfect piece of wire. And yeah, you guessed it, the result here is the exact opposite of the off state. In saturation, the transistor is just like a closed switch. The path between the collector and the emitter is now wide open, letting that main current flow with almost no resistance at all. And to make this happen, we do the complete opposite of what we did for cutoff. We apply a positive voltage to the base, which gets a nice, large base current flowing. This forward biases both of those junctions, throwing both internal gates wide open. The resistance plummets to nearly zero, and the transistor is now fully on. Okay, let's pause for a second. We have a switch we can flip just by using a little bit of electricity. This might sound simple, but this is the exact moment where raw electricity starts to become something way more powerful. It starts to become information. So let's just recap the two states real quick. In the cutoff region, the switch is open, no current flows. In the saturation region, the switch is closed and maximum current flows. Open and closed. Stop and go. Off and on. And this is the giant leap. This is the Rosetta Stone of digital computing. We can assign a number, a value, to each of those physical states. The off state with no current, that represents a binary 0. The on state with current flowing freely, that represents a binary 1. This is it. This is how we create the fundamental language of every single computer on the planet. Every single thing your computer does is built from this simple idea. By combining these simple on-off switches in really clever ways, we create things called logic gates. And then by combining billions of those logic gates, we build microprocessors, the actual brains of our modern world. And it all comes from a simple decision, 0 or 1. So we focused this whole time on the two extremes, right? The fully on saturation state and the fully off cutoff state. And that's because it's the key to all digital switching. But that does leave a pretty interesting question, doesn't it? What happens in that gray area in between? What can we do when the gate is neither fully open nor fully closed? Well, that's a whole other story.